point. The whole point of the video was I want to make sure you understand that if an object is rolling, and it has to be literally rolling, like this doesn't count as rolling. This is just spinning, okay? And this doesn't count as rolling. This is just moving. To be rolling, it's got to be rolling, okay? So if the object is rolling, it turns out that it is true that the rotational kinetic energy of your rolling object can be calculated by finding the kinetic energy of that rolling object and just multiplying it by this magic number b. Okay? So what is that b, you guys? What does the b mean? Okay, it's the fraction from that rotational inertia sheet, this thing, right? Okay? So at this point, so all of these little equations, like 1/2 mr squared, 2/5 mr squared, all of those are equations to calculate rotational inertia. Okay? But at this point in the chapter, you really don't ever need to calculate the rotational inertia. Okay? At this point, Tim, please, at this point, the only thing that you need that for is to figure out what your b is. Okay? So, I is b times mr squared. So whatever this b is what goes here. Cool? Okay, sorry, I don't know if you're talking about physics. But, all right, so is everybody okay with that? Okay, so let's see what that buys us. So, number 4. We can do this. Okay, so what do we got? So this is 7.3, number 4. Okay, so it says a bowling ball rolls at a constant velocity of 4.6 meters a second. So it's just rolling along at a constant velocity. Then it begins rolling up a ramp, which is inclined at 45 degrees. We want to know how far up the ramp the ball is going to get before it stops and comes back down. So I'm picturing this. I'm picturing a ramp that looks like this. It's inclined at 45 degrees. Here's my bowling ball. Here's my bowling ball. It's going to go up, slow down, stop, and come back down the hill, right? Okay? So all of these problems are conservation of energy problems, all right? Anytime you're dealing with an object rolling up a hill or down a hill, it is conservation of energy, all right? For now, I'm going to ask you to just take my word on it, and at the end of the hour, I'll talk a little bit more about sort of why, okay? But for now, let's worry about problem-solving strategies, okay? So, what turns out to be true then in this instance is that the total energy that the ball has at the bottom is equal to the total energy that it has at the top. Follow? All right, and what the problem tells us is that when it's at the bottom, it has a velocity of, is it 4.6 meters a second? What's the height at the bottom, you guys? 0. Okay, then when you get up here to the top, the velocity at the top is going to be 0, and we want to kind of figure out how far up the ramp it went, right? So do you guys agree that if I can find this height, then I can do a little bit of trig and find out how far it went? Everybody good? Okay, so like I said, it's just a conservation of energy problem, all right? The difference is, in the past, this would have been a sliding object. So it would have been true that whatever the KE was at the bottom would have equaled the GPE at the top, right? But now we've got this extra form of energy to deal with, specifically the rotational kinetic energy, right? So here is the idea. At the bottom, I'm going to have 2 types of energy. There's kinetic energy at the bottom, and there's rotational kinetic energy at the bottom, right? And those 2 numbers added up have to equal, at the top, what's the only type of energy we're going to have, you guys? GPE, right? So that's got to equal the GPE at the top. Follow? Any problems and lots of blank stares? Are we cool? All right, so let's plug in our numbers. Let's see. It didn't give you the mass of the ball, which I know is frustrating. If I don't give you the mass, it doesn't matter, so it cancels. Okay? So let's see. Kinetic energy at the bottom. Well, that's 1/2 the mass times the velocity squared, right? Plus, now how do I deal with that rotational kinetic energy? Well, remember, that was the whole point of this business. my rotational kinetic energy is equal to whatever the kinetic energy is times B. All right? So honest question, because I've lost my sheet. What type of shape is this ball here? Do we know what it is? What kind of ball? Is it a ball or a hoop or a... Number 4, a bowling ball. Bowling ball is basically a solid sphere, right? You can ignore the holes, but right? Okay, so because it's a bowling ball, that means it's a solid sphere. So I, for a solid sphere, is, I think it's 2/5 mr squared. And therefore, B is 2/5. Okay, that's the only thing you need from that sheet for this problem. It's just that 2/5. Are we good? Okay, so let's see. So that means that my RKE should be my B, which is 2/5, times the KE, which is 1/2 m times 4.6 squared. Does that make sense? So this is B times the kinetic energy, right? Follow? All right, and that's got to equal the GPE at the top, which is just m times 9.8 times the height at the top. Cool? All right. So what do you notice? All the m's cancel out, right? As a quick side note, one of the things I commented on in the video is you could, if you wanted to, rewrite this as 1 plus b times the KE. So I don't know if this helps any, but some people were doing it this way. 1 plus 2/5 times 1/2 m times 4.6 squared. You can do it that way too if you want. I don't know that it's any easier, but it works. Okay. So anyway, like we said, the m's cancel out. And whether you do this or this whole mess here simplifies to give you something. I wonder what it is. So I want 1/2 of 4.6 squared plus, what, 1/5 of 4.6 squared? So if you simplify that using either of these two green lines here, you get 14.8 equals 9.8h. Let me pause there for a minute. Did I lose anybody in any step of that? Everybody's good? Okay, so divide both sides by 9.8, and your h is going to turn out to be like 1.5 or something like that, 1.51 meters or something. And then you can do a little inverse trig to find your hypotenuse. Cool or no? So then you just 1.51 theta x. So x is going to be what? 1.51 over the sine of 45. What was the answer? 2.14. Cool? Probs? All right, say it again. Problems? Okay. Number 5 is similar. The only difference is you know the height and you're looking for the velocity. Okay? So basically, where you've got these 4.6s, you're going to have a v. And so you just solve for the v instead of solving for the h. So that is the deal with number 6. As I said, I will post that on my website. Any questions before I do 5? Pretty good. Alrighty then, number